All right, it's time. First thing is I received a question from number 5 in WebWork 1.9. Okay. Basically, what you have here is you have a container. You start with 90 kilograms salt with 1,000-liter water. And then you start pulling it at 8 liters per minute of salt water with a concentration of salt to be 0.8 kilograms per liter. Meanwhile, we have a drainer, which gets water out of your container here, and it's doing things at 2 liters per minute. Now the question is, you want to model AT, which is the number of salts in the container, okay, in terms of kilograms. So that's what we want to do. The first thing we want to do is set up the initial condition, A0. That means before you start all the whole process, how many salt do you have? Clearly, in this case, it's 90 kilograms. Now you want a differential equation. Then you just need to write down A prime T, which is the changing rate of your mass of salt per minute, in this case. And it's pretty straightforward. It should be the salt coming in and the salt coming out by the draining. Okay. If it's more coming in and more what is coming out, you have a positive rate. Otherwise, you have a negative rate. Okay. So eventually, what do you have? You have the salt coming in. That comes from this part. You have 8 liters per minute, and for each liter, it has 0.8. So together, it's 0.8 times 8. That's how much salt is coming in. How much salt is coming out? Well, clearly, it should be the concentration times the volume per minute. The volume per minute is 2. The concentration technically is changing because as time goes by, you have salt coming in, you also have water coming in. Okay, so how do you solve this? Well, concentration is nothing but salt divided by water. How much salt do you have right now? That is going to be AT itself. How much water do you have? Well, you started with 1,000 liter. Now every minute, how many comes in? 8 comes in. And every minute, 2 comes out. So together for every single minute, you have 8 minus 2, which is 6 liter water coming in. So the total water in the container keeps increasing at a rate of 6. Therefore, what you should put here is 60. Okay. That would be the water divided by, that would be the salt divided by water, which gives the concentration. And then if you have this concentration, which comes out at 2 liters per minute, this will be the total salt coming out at any moment. Together, this is the setup of how to do the differential equation. Of course, we wanted to do it in the way the WebWork wants it. So let's move everything on the other side. That would be what WebWork wants. All right. With that in mind, now you want to go ahead and solve it for C. Okay, you want to find the integrating factor. Now we know we have to move everything and rewrite it in a format identical to the thing we had in class, YT, Y, and T. So now it's clear. We have to find a mu, where mu prime equals mu times 2 over 1,000 plus 60 times this one. Okay. Solve it. We can pick any c, so let's just pick c to be 0. So we got this. And then u is nothing but e to the ln no, 1/3. Something doesn't feel right. Did I have a 2? I guess I have a 2. Okay. Now with that in mind, we want to put it back into the original thing. 1000 plus 60, 1/3 times a prime t plus 1000 plus 60, 1/3 times 2, 1000 plus 60, a equals 6.4. If you don't believe it, you can quickly verify it, such that the derivative of this one will be exactly this one. So basically what we have here is a mu a prime plus mu prime a. Okay. Therefore, we have a product rule. You can verify that. Otherwise, you find the wrong integrator. But they have already verified it. Here's a perfect product rule. Here is this thing times. Okay. The rest is try to take the integral. Let's see, at equals something. Yep. So the rest is try to find the integral. Just call it a equals 6.4. We definitely have this. Therefore, we should have a 3/4 times a 1/6. A equal 0.8, 1000 plus 60, 4/3 and 1/3. After you divide, they become 1. Yeah, that's roughly what we got. Simplify a little bit. 800 plus. Finally, to finish, you have to plug in the initial condition. Therefore, if you plug in 0, a, which is 90, equals 800 plus c over 1000, 1/3. Okay. C equals negative 7971 times 1000 to the 1/3. Okay. Finally, AT 4.8t plus minus divided by minus 800. Plus 800. Doesn't feel right. But let's check. Mm-hmm. 4.8 T minus 710 times 1,000 to the 1/3 divided by 1,000 plus 60 to the 1/3. Finally, plus 800. Cool. All right, last question. What's the limit as t goes to infinity of the concentration? Okay, so limit x goes to infinity, t goes to infinity. Concentration should be AT divided by the water. The water is nothing but 1,000 plus 60. Okay, that's the concentration, which is limit t goes to infinity. 4.8 T minus now this reduced to a calculus 1 problem. As t goes to infinity, this goes to 0. Okay. The leading terms will be the first one and this one. So finally, the answer is going to be 4.8 divided by 6, which is 0.8. That will be the answer for the last one. Which kind of makes sense, right? Think about what's going on. Originally, you have some thought. And what you do is you just keep pulling something inside with a fixed concentration 0.8. If you let t goes to infinity, whatever in here doesn't really matter anymore. Because eventually, if it's a little bit higher than 0.8, you will make it smaller. If it's a little bit smaller than 0.8, you will make it bigger. So eventually you will stay at this concentration. So everything stay at equilibrium and never change anymore. So as t goes to infinity, without doing the computation, you should know it should be exactly the same as this. Otherwise you would adjust such that it is this. Okay. By then, you reach equilibrium. And if you think about it, you can really get it by setting this one to be 0. Okay. We skip that. But if you set this one to be 0 to find equilibrium, it's pretty easy to see. Sorry, not this one. Where is it? Yeah, setting this one to be 0. Okay. You will be able to find equilibrium easily. All right. The answer is 0.8. Not surprising. Sounds good? Everything here? Okay, I would say the harder part is trying to write down the equation. After that, it's purely just standard mechanic, finding the integrator and finish it. Second thing which becomes super interesting, that is, how general is this differential equation? Well, if you take a look at what we just write down, for integrators, you basically have y prime plus aty equals bt. Okay. So somehow it tells you it works for anything that your changing rate is somehow linearly related to your current value. That is, your y prime is linearly related to y. If you think about that case and try to look for applications, you'll find that is actually very, very popular to see in real life. Okay, a lot of models follow this way, like the concentration one. So that is good. All right. Any more questions regarding number 5? Okay. As far as you can see, we don't have a lot of web work, only like a few questions per section. And if you don't find any web work for a certain section, that basically means I couldn't find any meaningful web work to put there. Okay. So for some of the sections, if you don't have a web work, I think you should test yourself with your textbook problems. I put a list there, especially for the sections which does not have a web work. You should practice by yourself to make sure you get the concepts. Of course, the ultimate challenge is in the writing project. They're really challenging. And through that, you can really get the core of what we're trying to do with differential equation. All right, I think we finished. Now 2.2, systems, actually geometry of systems. We talk about two things. Well, if you have a system which look like this, dx over dt equals fxy, dy over dt equals gxy. Okay, we have the following comments. The first one is this is autonomous because there is no t, only x and y. Because of that, we can do slope field. But in this case, it's not slope field anymore. It's direction field. Number 3, for this, we can do the equilibriums. Okay. That's what we had. And then we tried it on 3 different examples. The first one is predator and prey. We start with example. We try to calculate the equilibrium and everything. So basically, the direction field, we can code it, and the solution curve looks like something like this. We have equilibrium here. We have equilibrium here. That's case 1. Case 2, we did the same thing, except we assume a logistic growth for the rabbits, which is 2r 1 minus r over 2. Everything else stay the same, and this is more realistic. What we end up with is we have 2 equilibriums, and no matter how we start the solution, it always eventually goes to here. Okay, which is quite different from what we have here. So eventually we have a stable population, not like this one. This one eventually we have a stable pattern, but that pattern is periodic. Sometimes the fox is more, sometimes the rabbit is more, okay? And you repeat this pattern again and again and again, which is dynamic. But for this one, you stay at a fixed population, and that's it. Number 3, we did the harmonic oscillator. Y prime prime equals negative k over m, y. And we change it. We change it to be a system. Y prime equals v, and v prime equals negative k over m, y. We try to draw the direction field. We find several interesting things. Number 1, we have 1 equilibrium. Number 2, the trajectory in the phase plane is like a circle going this way. Okay. It may be an ellipse. It may be a circle, depending on what your K over M is. In this way, we kind of have a nice relationship between the velocity and displacement. That is, they all shake like sine and cosine. Okay. And their phase trajectory is something like this. I think that's good enough for a standard example of how to draw direction field. So we stop here. Anything else, if you feel like it's still shaky, try the homeworks and try to draw several more direction field. After that, you should be able to get how to do this. Cool. Now we go to 2.3. Harmonic oscillator is very, 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 very important. So we want to study more on this concept. Moreover, we don't want to study the ideal case anymore, which means no friction. We do want frictions this time. So we talk about the damped harmonic oscillator. Okay, this time we want to write down all the details of how to derive a harmonic oscillator. First, undamped. No friction. Of course, we're talking about one dimension, so relaxation. You put a mass here, you let the spring to be relaxed, nothing happened. Now what you do is you stretch this one, or you compress this one, doesn't really matter. That's your initial condition. Now you can see if you use your hand to hold this one, you are going to have a force going this way. That means as soon as you release your hand, the whole thing is going to shake back. Okay. Now we call this X. Let's do it. Did the book use X or Y? The book used Y, so we call this Y. So we can say Y stands for the displacement from 0, which is the relaxation point. Y prime is going to give you the velocity of the oscillation. And of course, Y prime prime should give you the acceleration. Okay. Then the beauty of setting this thing up is we can use Newton's second law. Which is called F equals ma. And we can have ma to be my prime prime. And fortunately, the force F is closely related to your displacement. The bigger the placement, the bigger the force. The further you stretch the spring, the bigger the resistance force. Okay. This is given by Hooke's law. Hooke's law in 1D. Okay. Here, your M stands for the mass. Your K stands for the spring constant, which basically tells you the strength of the spring, quantified by how much force you receive by how much you extend in distance. The bigger the number, the stronger the spring. This should be Y. All right. That's what we have for harmonic oscillators, which is undamped, no friction. We already solved this one last time by transferring it into a differential equation, like I just draw. The phase trajectory looks like this, with the equilibrium like that. Done. Y prime. Sounds good. Now we want to do the damped. MA equals Hooke's law. This time we are going to add in the friction. The friction should be proportional to your velocity. The faster you move, the bigger the friction. Okay. This B is just the friction, or let's say that constant or coefficient, however you want to call it. And of course, we should put a negative sign here because the force you receive from friction is always to the opposite direction of your traveling. If you go to the right, the friction should actually slow you down. So it always slows you down. It always damp you. It always absorb energy. That would be the formula. Okay. Of course, since we have many terms, usually when people do that, they put it into the standard form, which simply just move everything to one side. So we all have plus. And the second, you have a nice order of things. You have y prime prime, y prime, and y. And then someone will go even further by dividing m on both sides. Then you will receive this. And then finally with this, where P equals B over M and the Q equals K over M. Okay, whichever way, you should realize this is basically a second order linear ODE. All the derivatives of y, including the first and second, are included. Moreover, all the coefficients has nothing to do with t. Therefore, you can say with constant coefficients. That's a mathematical way of representing what we're dealing with. That also means later, as long as you see a second order linear differential equation with constant coefficient, it does not necessarily come from a harmonic oscillator. But we can treat it as a harmonic oscillator. Okay, it's general enough. Sounds good? Now we're ready to solve it. Of course, when we say solve it, we technically means see the geometry, do the direction field. Okay, we cannot technically solve it yet. Geometry of the system. Now let's go back to this one. Okay, we still prefer to write everything in that V equals Y prime. Okay. Then Y prime equals V, and the V prime, which is Y prime prime, equals negative P V minus Q Y. Here V is just Y prime. Okay, here. You can go ahead and try to find the equilibrium point. You can go ahead and try to plot the direction field. Of course, to better see it, let's better code it. It's taking a while to open my, okay, yeah. It's 2.3. Okay, it's here. Continue. All right. Let's see. Yeah. Dropbox. Okay, this is what we just put there. I picked some random P and Q. Okay, P equals 3, Q equals 2. Now let's go ahead and solve it. Try to compare with what we had before. Remember, what we had before was a whole circle. Nothing just repeated itself. Okay. But now what we have is actually a trajectory which just spiral as before. But as you spiral, the radius of your circle becomes smaller. Therefore, you cannot have a complete circle after a whole cycle. You become a smaller circle as you move, which gives you a spiral pattern. And eventually, you won't keep oscillating. Eventually, you stop somewhere because you're damped. The friction eventually is going to absorb all your energies and transfer them into heat. So the whole thing stops. Okay? That's basically what we got for damped harmonic oscillator. Make sense to everybody? Okay. A second thing becomes super interesting. That is, you can actually have two different P and Q. You pick P and Q to be 3, 2. And then you pick P and Q to be 1 and 2. By playing with the numbers, you can compare these two graphs. And then you see, by picking different number of P and Q, you kind of have two different behaviors. The first one, if I'm going to guess, looks like exponential. There's no oscillation. Right? You don't even pass the relaxation. Because you have a big frictions, you cannot even complete one cycle of oscillating. That's one way. Second, you do have an oscillation, but your oscillation becomes smaller and smaller and smaller and smaller And again, that is by absorbing your energy. So which one do you have? A straight one direction one, or actually you oscillate for a few times until you spiral into the trajectory? That will depend on how you pick your P and the Q. Okay, in general, a bigger friction is going to create something more like this. Will stop you from oscillating. And if you make the friction to be small, you can oscillate more. For example, if I take P to be 0.1, keep the Q. Then clearly you see, okay, I can oscillate even more. I can probably complete 5, 6, 7, even 8 cycle until I finally reach the point there. With this thing here, we cannot even see that thing stops. So let's do a longer time. Let's do for E 50. So let's do maybe 100 is going to be good enough. You can see eventually that thing stops. Okay, and you have something which stops there, but you keep spiraling until you actually fulfill all the places here. Now, if you keep increasing your friction, let's make it 1. You oscillate only a few times, then you hit this. Let's make it 5. Now you can see you don't even oscillate because your friction becomes too big. You stopped after, actually not after, right before your first oscillation. You just stop there, and you produce something that looks like exponential decay. All right. Any questions regarding the geometry? Cool. So let's summarize what we just observed. First thing, P equals 0, no friction. Number 1, T, Y, you have oscillation. Just keep going. Phase plane, you have a circle. Just keep going. And you go forever. Now P is bigger than 0, but small. Let's just do small p. Now you have friction. What's going to happen? What's going to happen is you start to shake. Actually, I shouldn't do this. I should do starting from something non-zero. Okay. For the second one, you should shake. But as time goes by, you should shake smaller and smaller and smaller and smaller. And eventually you stop. All your energy got absorbed. Moreover, if you think about it, this one never stops right away. This one just keeps oscillating, but the oscillation becomes smaller and smaller and smaller. So what you really should do is you should take the sum of all the energy of each oscillation. And you can see this energy is going to be infinite, have infinite many terms. So you need to take the sum of an infinite series to be a finite number. Okay, you don't just shake, 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 and suddenly you just stop shaking. No, you just keep shaking, smaller and smaller and smaller, which you cannot even tell it's shaking, but it's still shaking. And eventually you reach some constant. Of course, the trajectory in the phase plane, this time is going to be still a circle. Okay. But as you go counterclockwise, your circle becomes smaller and smaller and smaller. Therefore, that gives you a spiral. And keep going. Eventually, you reach 0, 0. Okay. Corresponding to the spring, it's very easy to see. This one is shaking. Shake, 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 something like that. So totally makes sense. Finally, big P, big enough, bigger than 0. Huge friction. Then what's going to happen is, before you will be able to do this and just come back. Now you cannot even finish the first cycle. You just do this and that's it. You cannot even break through. Okay, there's no way because the friction is too big. Judging by the trajectory, this was the original. Now you have something like this. Okay. Finally, you have something. You cannot even pass this and just go right here. You cannot go beyond that because you don't shake. Yeah, let's not do something fancy, just like something like that. Sounds good? Qualitatively, this makes sense. It's not hard either. Now, finally, we want to go ahead and solve it. Because, I mean, this is really the easiest that we can see. Okay. Now we are going to go with this form because it looks nice. I mean, seriously, if you want a system, this is probably the easiest one you can have. Number one, you only have constant as your coefficient. Number two, for a system, you need to have at least 2. And this one gives you 2, not 3, not 4. So this is probably the easiest one. To make it more straightforward, let's pick P equals 3, the Q equals 2. So you're basically looking like this. All right, let's solve it. How do we solve it? We make a guess. We guess the solution looks like this. Okay, where S is a constant. Why do we guess so? Well, by this graph, this looks like exponential. So I'm going to guess it's exponential. And for exponential, I just need to know the rate. Still okay? Now to finish, we just need to find S. If we know S is 2, period, done. All right. So if we assume this is the equation, this is the solution, we just don't know S, we can pretend we know it. All we need to do now is, this one should satisfy this differential equation, right? So we should just plug it in. Prime prime, y prime, so this one. After that, do the derivative. Well, it's not hard because when you take the derivative of exponential by chain rule, you just time this constant in the front. And for this one, you just do it for twice. Still okay so far? What do you see? Well, number one, this guy is a common term. I can take it out. Second, two things times together equals 0. Then either this one is 0 or this one is 0. Good so far? Will this one ever be 0? E to anything? No. Then this is not 0. So what's left? This has to be 0. What was your job again? You want to find S, which satisfies this differential equation. For what kind of S this will be true? You can solve it by solving a quadratic. Therefore, the solution is y equals e to the negative 2t, or y equals e to the negative t. These two definitely is going to work. Make sense to everybody? The key is we guess the solution looks like this. Why do we guess so? Well, for now, just take it for granted. We just guess things to be like this. But once you guess things to be like this, you plug it in. Eventually, you will end up with a quadratic equation of S. You finish it, you got S. Once you have S, you have two solutions at least. And you don't have to check. They definitely is going to work because that's how you construct it. Make sense so far? Okay. Only for this example though, but we solved it. That's why I hate this book. The book stopped here. Okay. So what I want to do is I want to just, there's nowhere I can do this again. They just don't cover this in the book, which is ridiculous. But I want to show you some deeper understandings behind this. So just follow my question. Try to think about how to answer the questions. Number one, you have two solutions. Sounds good. Do you have a third solution? Do you have a fourth solution? How many solutions do you have? Okay. What I claim is the general solution the general solution looks like this. Or let's say all possible linear combinations of these two solutions. Sounds good? So how many solutions do you have? Infinitely many. Technically, how many? A two-dimensional solution set. Okay, it's a space. It's all the linear combinations of two linearly independent functions. Still okay? Why linear combination work? Because this equation is linear. Then if two things and homogeneous, this will guarantee if these two work, then all the combinations work. Because the original thing was linear and homogeneous. Okay. Second, even though you found all these, which is great, you found a lot of solutions. How do you convince people this is enough? How do you convince people there won't be a C1 plus C2 plus a C3 times something else? That's another thing. Now you can see this is the second order. Linear ODE. That means if you want to have some constant which can vary freely, you only have two. You take integration for once, you have a plus c. You take integration for twice, you have plus c and a plus d. So not only 2 is good, 2 is enough. There's no more than 2 because I'm a second order differential equation. Sounds good? So by some lucky guess, you guess the 2 solution. Then you realize, okay, all possible linear combinations of these 2 will also be solutions. Number 3, there's no other ones because 2 is already everything. There can't be a third. Otherwise, I can't be second order. Okay, so that's all. You only need to linearly independent solution. I just say, yeah, 2 different solutions. Yeah, that's not a good word. That's already completely linearly independent solutions. You won't have 3 because you're second order. Sounds good? That's number 1. Number 2, what did we just do? We did this. Okay, we let y equals e to the st. Okay, what we produce? We produce s squared plus 3s plus 2 equals 0. And then we solve for s, we find all the solutions. Sounds good? What if it's not 3 and 2? It's just p and q. You actually don't have to do it, but if you want, you can certainly do it. You do the derivative for twice, you get an s squared. You do the derivative for once, you got an s. You do the derivative for 3 times, you got s cubed, right? So eventually, you will always receive something like this. It's not going to be 3 and 2. It's going to be p and q. By solving this, we have s equals to -1 and s equals to -2. So happily, we have 2 solutions. Beautiful. Okay. But now PQ can be anything. Now you need to ask yourself, we were just lucky. We got 2 real solutions before. But if you solve a quadratic, how many different cases can you have? Number 1, you can have 2 distinct real solutions, right? Number 2, you can have only 1 repeated solution. Still okay? For example, like s squared plus 2x plus 1 equals 0. You solve it, you only have s equals to -1. To finish, however, you need 2. And then all the linear combination of them. You are going to have trouble in this case. Still okay? Number 3, it's also possible that if you do this, there's no real solution. It's possible. Okay. So what do you have instead? You have a plus and minus bi, complex solution. Roots. If it's -2, -1, you know 2 solutions. But if you know this, how are you supposed to write it into exponential? Can you put a complex number on the exponential? If you put a complex number on the exponential, what do you mean by that? Make sense so far? Okay, so we just handled the easiest case. We still have 2 more cases to think about. This case is easy. It's called degenerate. You just manually create another one. This case we will talk about next time. That's where you get the cosine sign. If you just follow what we have here, you're only going to have exponential. But remember, we have cosine sine oscillation, right? That must come from somewhere. We'll pick a special P and Q. They come from here. All right, that's all for today.